Should I not lecture? And you already read all the notes, so do you have questions?
Glossed over them a little bit. Actually, one question about operators. Can an operator also be an integral?
Yeah.
Yeah, you can use an integral as an operator.
Sure. So just general rule is the operator takes a function and produces a function.
Yeah.
And so if you define the operator like this, for example, then you can think of the operator as an indefinite integration. If you put x squared here, then the result will be x to the third divided by 3, right? You can also make an operator with definite integration, or the integration that we say use we can say from minus infinity to plus infinity. So you put the function here and say you multiply whatever result is by a function, right? So then O1 f of x is f of x multiplied by the integral, right? So this is another function, g of x, which presumably is f of x multiplied by some constant coming from the integration. Right, so you can play with this, well, the integrals, derivatives, making the operators.
Will we possibly see something like that on our tests, or is that beyond scope for us?
No, we usually don't use any of these operators in the quantum mechanics. One operator that actually we talked about, but I didn't formulate it as an operator. Imagine if someone asks, okay, what is operator that if you give it a function, or more than our usual way of writing a wave function, psi of x, then it will create function psi n of x, so that no matter what psi of x is, the integral of psi n star psi n is equal to 1. Right? So the question is, what is O, so that when you give it a function, then it will produce a function, so that when you put this function, the resultant function, into the integral like this, you will always get 1. So that operator you can think of as a normalizer, right? So you give a function and it normalizes the function. Normalizing means that this pretty much is the same as if you think of the function as a vector, then this means that the inner product of the function with itself is 1, so it's like a normalized vector. Okay? So how do we formulate such operator? Well, all you need to do is, so how do we obtain psi of n? Without any operators in mind, what do? We take the function psi of x and divide it by the square root of the integral psi of x star psi of x d of x, right? Minus infinity plus infinity. So that's the prescription to get a function that is normalized now. You take a function and divide it by square root of integral of its product. Absolute square, to be exact, right? So this is what we talked about. Now you can think of it as an operator an operator would be, there is this awkward notation where I put dots where I'm supposed to put functions, because operator accepts as an input a function, and then, but it makes the whole thing a bit abstract. Nevertheless, you can write this operator as, in numerator you put a function, that's why I put the dot, then divide by square root of integral from minus infinity to plus infinity, and then inside the integral I put this absolute square sign and the dot, so whatever function you have, you put that function in the numerator, and also you put that function in the denominator inside the integral, right? So that will be our normalizing operator, right? So you can think of normalization procedure as an application of the operator which acts as I described. Okay? So any operation, differentiation, integration, normalization, you can write as an operator acting on a function. Very natural language. Right? It's like operators generally is objects that do something to functions, right? So the difficulty of quantum mechanics is that we need to work with functions. And naturally, in order to get any prediction, we need to have a procedure. How do we get numbers out of functions? Because numbers eventually are the results of any experiments. So we need to know how to go from functions to numbers. And that's what this course is about, pretty much, right? So we will learn how, if you are given a function, how can you predict the results of any experimental measurement, which if done on the system, will produce a certain experimental outcome, and quantum mechanics kind of knows how to predict what the outcome is. That's why it's powerful, okay? Because it can predict without doing experiment. Now, we talked before why operators are so important, because any property in real life, in quantum mechanics, has an operator, right? And say the kinetic energy, as an example, has an operator T, and there are actually few operators we will be dealing in this course, so there will be not many. So hopefully at the end of the course you will know all of them by heart. And so the kinetic energy operator is just this constant, negative constant, minus h bar squared divided by 2 masses, and then it has a second derivative if we work in one-dimensional space. For simplicity, it's just a second derivative with respect to our x coordinates. And so then, once we define operator, in order to predict the results of the measurement, we already kind of formulated last time that any measurement will be what? Guys, remember anything from the previous lecture? Why operators? Like, why do we study operators? Yeah. That's right. They can. Every operator has eigenfunctions and eigenvalues. So what are these guys? Eigenfunctions and eigenvalues. Yeah. Anyone else? Mathematically, what are the eigenfunctions are? Yeah. So let's just go to the basics. What is an operator?
Change a function to an object.
That's right. So it's an object, takes a function, gives you back another function, right? It's like, what is a function? It's an object that takes a number, gives you back another number, right? Operator is one level up. It takes a function and gives you back another function. Simple example of an operator, differentiation. You put a function inside, operator operates on a function and gives you another function, right? So what just happened? I gave an operator a function that looked like this, right? Parabola. What did it give? What did it give me back? A function that is linear, right? So looks like this. So it's almost like unbent parabola and made a straight line. This is magic, right? So this is what operators do. What they do, they take a function, parabola, and then they unbend it into the, in this case, straight line, right? Or if you take another function, x to the third power, what d over dx will do to it? 3x squared, right? So it will bend this branch into the, essentially, into the parabola now, right? So it changes the shape of the function. It takes a function and gives you back another function. Now, it turns out that there are magical functions which are called eigenfunctions. Okay? They're magical because what is magical about it? So say if we have d over dx in our operator, and that magical function, which we call eigenfunction, and I haven't defined it yet, but I will. Eigenfunction. That function, when the operator acts on it, it will produce the same function back. Okay? So you may ask, where is the magic? Well, the magic is, if you look at this operator, what can it possibly do to a random function? To a random function, it can do random stuff. Like you put the parabola, it gave you a straight line after operating on this function. Now what happens here, you have a special function. When you put it into the operator acts on it, function comes back the same way it was in the beginning. This is surprising because we just saw that for a random function x squared, d over dx will change its shape completely. Its own mother will not recognize it anymore, right? So from parabola, straight line, from the hyperbola, you get the parabola. So there are lots of changes going on just because of the differentiation. Now these special functions, eigenfunctions, they are not changed at all. Okay, that's why they are so special, right? And in this particular case, if you say, let's put the exponent, right, as a function, how does the exponent look like? It looks like this, right? F of x. And so the magical thing about the exponent, if you differentiate the exponent, you get back exponent, right? d over dx of the exponent equals e to the x. So that means we can say that exponent is f of x, and in this case lambda, which is an eigenvalue in front of the eigenfunction, it's just 1, right? And so as you can see, you differentiate the exponent and the shape didn't change. You get back exponent. Now you can keep playing with this concept, and you can put any function like this with the exponent and the constant in front. All right. So then d over dx will give you minus alpha Although we got something non-trivial here, alpha can be anything, 100, minus 100, right? But this is just a constant. The shape of the function is defined by its dependence on argument, and that dependence didn't change. Before we saw if you put x squared, you get x, right? So the shape changed, but for this special class of function, which are eigenfunctions, nothing changes in shape. All right. So my favorite example, you've maybe seen this TV show called Biggest Loser. All right. So people change shape there. Right. They go under the severe training, and they change shape. All right. So they are not eigenfunctions with respect to those operations. Now think about what's going to happen if a trainer, there are trainers, right, in this program. What if a trainer is put through the same program? Well, nothing will happen to him or to her because, well, they're already in shape. Pretty much will be no observable change. The shape will be the same. So they are kind of eigenfunctions of that operation. Okay? More than that, they work with the participants and you don't see big difference in their shape. Maybe in attitude, but not in shape. Shape stays the same. So they are kind of the analogs of eigenfunctions to the operations which are training in this case. Right? So operators, in our case, they change generally the shape of the function, and there are such special functions which are eigenfunctions, and this they are special because they don't change the shape when the operator acts on them. Okay. Now for physical, this is all math, right? So this is all math. And physical reason why we are so making such a big deal out of the eigenfunctions is because the eigenvalues that are coming out of the eigenfunctions when the operator acts on them, these are the numbers that are coming out as a result of the experiment. Okay? So therefore, if every property, right, in real life has an associated operator, and every operator has its system of eigenfunctions and eigenvalues, right, then the eigenvalues are the results that are coming as a result of the experiment done by when you measure a property associated with the operator. Okay. Now this is all very straightforward. So essentially, if you measure the kinetic energy, all you get is the eigenvalues corresponding to eigenfunctions, where T acts on this eigenfunctions, right? And then gives you these eigenvalues. These are results of the experiment. Now, this is all very simple and straightforward. The difficulty, there is a little difficulty. And the difficulty is that we always will be dealing with a wave function, right? So our system, whatever we decided to consider, this piece of chalk, this table, or electron, right? So all these objects, they are defined in quantum mechanics by a wave function. And if we decide one day to study what is the kinetic energy of this object, then, well, the first step is we define the operator. Say we decided to study kinetic energy, so that's why the operator that corresponding to that property is the kinetic energy. Right? Then we act with this operator on a function of the system that we're interested in. And when we act with an operator on a function, we generally get another function, phi. Right? this phi can either be constant multiplied by the original function. That would make original function an eigenfunction of the kinetic energy operator. Or phi is not constant multiplied by original function. Okay? And so there are these two cases which are treated slightly differently. Okay? Because after all, we want to know if we take a system which is in a state psi of x, and we measure kinetic energy in this situation, right? What will be the result of this measurement? It turns out that if the wave function is an eigenfunction of our operator, then the result of the measurement is just an eigenvalue. Okay, so that's very simple. Okay, but if the situation is that our function is not an eigenfunction of the operator, then the result of the measurement is a little bit more complicated to figure out. But we will do it today on the simple examples. Now let's just first consider the first case, number 1. In the case number 1, we have our function, the system, eigenfunction of the operator. Okay? So let's just see the example of that. Imagine our eigenfunction is the exponent of I kx. Right? So where does this come from? Just for the sake of example, it's stated as an initial condition. Like that's given function, right? So say it's a plane wave, free particle, no potential. It turns out that this is this could be an eigenfunction. Sorry, the function of the system. And then the question is, what is the momentum of this system of psi, and what is the kinetic energy? Of psi. Okay? So there are two properties, momentum, kinetic energy. So first things first, if a problem like that is formulated, you need to figure out what is the operator corresponding to the property. So for the momentum, it's I with minus multiplied by h bar d over dx, right? And kinetic energy already is given here. Now, the second step is we check whether an operator has this wave function as one of its eigenfunctions. So for that, all we need is to act with an operator on a function, right? So how do we do that? We write an operator, I h bar d over dx, and then the function I k x. So what will be the result of the differentiation and multiplying by a constant of this function? Anyone?
So just IK times the original function?
That's right. So it's very simple example. I don't know, what are you thinking? So it's IK comes out of the exponent when you differentiate. There is another constant minus I h bar, and then there is a original function I k x, right? So the only thing which is left is multiply the constants minus I multiplied by I, together that is 1, because I times I minus 1, and there is another minus 1, so it's 1, right? So h bar k form another constant, and there is the ikx, right? So overall, what we got is, this is a constant, because k is a constant, h bar is a constant, 1 is a constant, and the original function, right? So we have h bar k multiplied by original function ikx. What does that mean? Does this mean that the original function was an eigenfunction of the operator? Yes or no? Who thinks yes? Good. Majority. Yeah, so that's an eigenfunction. This is lambda, pretty much the prefactor that we get after applying the operator, momentum in this case. And so that means if we take this function and we measure momentum, we just shown that that function is an eigenfunction of the momentum operator. Therefore, according to the quantum mechanics, this will be the result of the measurement. Okay, very simple. Now you can do the same thing now with kinetic energy. Let's see what's going to happen if we take the same function, now a different property, kinetic energy acting on eikx. It's minus h bar squared to m eikx, differentiated twice, right? So we differentiate the exponent twice. Every time we differentiate, ik will come down, right? So minus h bar squared divided by 2m. That constant should not be forgotten because that's the part of the t operator. And then we have ik squared, right? And we shouldn't forget that doesn't matter how many times do you differentiate exponent, exponent will stay exponent, right? So exponent will stay there. That's why exponent is the main candidate for eigenfunction of any differential operator, because no matter how many times and how you differentiate the exponent, exponent will stay there, right? So that is kind of what we need from the from the eigenfunction. When operator acts on it, the function stays. Okay, so then now you can see where it all goes. So this is minus k squared because I squared is minus 1, right? So, and this minus 1 here, so we got k squared h bar squared divided by 2m as a constant in front, and ikx as a function. So we acted on a function with an operator. We got a constant, which is an eigenvalue, and a function back, which shows that this is an eigenfunction of this operator. So the eigenvalue, lambda, again I'm calling it all lambda, but this lambda and that lambda are different lambdas because they are eigenvalues for different operators. And so if you measure kinetic energy with the apparatus, the arrow of the apparatus will point to k squared h bar squared divided by 2m. Okay, so that is a number that you will see if you measure kinetic energy. And this number, h bar k, you will see if you use another apparatus to measure the momentum. Okay? And so for both of these properties, this exponent of ikx is an eigenfunction. Okay? And that's the easy case. Any questions about it? I say it's easy case because just to make it easy, what I did in advance, I've chosen a function psi that is an eigenfunction for both operators we are looking at, right? So in that situation, all you do is you check that it's indeed an eigenfunction, you apply operator to a function, you get the eigenvalue, and that eigenvalue is the result of the measurement. Okay, so you can predict the result of the measurement if your function is an eigenfunction of operator. Of course, one difficulty here is that different operators have different eigenfunctions. You don't know for sure in the beginning that whatever function I gave you is going to be an eigenfunction of that operator. So you need to check. But the simple situation is when you check and it turns out that the function you got is an eigenfunction of the operator, then you can predict the result of the measurement very quickly. Okay? Now, more interesting situation. More interesting situation is number 2, where your function is not an eigenfunctional operator. So what do you do then? Okay, and to create such example, let me give you a function which is x times x minus 2. And that is for x between 0 and 2. And then it is 0 for x outside of the 0, 2 range. Okay, so this is our function. And you can already see how does it look like. Say this is 0, this is 2. It's kind of a parabola, right, with mainly kind of going upward. And it is 0 outside of 0, 2 range. Maybe strange that the function looks down, right? So like the function is mainly negative, but there's nothing strange here because function itself has only meaning through its probability density, right? And probability density, you need to multiply function by itself. That would make things go up, right? And so it really doesn't matter whether you take this function or alternatively you can take 2 minus x multiplied by x and 0, right? So in these two functions, they give the same probability density, psi prime, say, and this function would look like this. But probability density wise, when you take psi square, that's the physically meaningful part. That part will be the same for both functions. Anyway, so let's see if we decide to work with this function. And the question we're asking is, what if we measure kinetic energy? We already worked with this operator. And say we want to measure kinetic energy again. Well, the first thing you want to check is kinetic energy acting on that function, psi of x. Does it give you lambda psi of x? Okay. So the simple answer to that question, well, you just differentiate, right? So you have a function to differentiate. The kinetic energy is an operator that differentiates twice. The function has x squared, and so when you differentiate twice x squared, you get a constant, right? So it seems like a good thing. We got a constant, but the bad thing is that, well, for this to be true, you need to have your function back times constant, not just constant, okay? So if we act with t, d squared dx squared, we act on x squared minus 2x. That's what will happen if you open the brackets, right? So then the result of this will be minus h squared divided by 2m and multiply by 2, right? So 2 cancels 2, and the final result h bar squared divided by m, right? So we got not constant multiplied by a function, we got just a constant, all right? So that means the answer to this question is no. If we act with kinetic energy on the function I gave you, we're not going to get constant multiplied by a function. We're going to get just a constant. All right? So in the grand scheme of things, that means that the function we were given is not an eigenfunction of the operator. Right? So we are in this second situation. So how do we deal with this situation? And the prescription is actually quite straightforward. All you need to remember in quantum mechanics why eigenfunctions and eigenvalues are so important, because when you measure property, there is an operator corresponding to that property. An operator will always have eigenfunctions and eigenvalues. And the result of the measurement of any property for anything will only be eigenvalues. Okay? It's like no matter what problem you are given, the only thing you can say about it is kind of combination of words of language that you know. Really. Like, you would be communicating on the language that you know. And this is the language of the operators, essentially. They communicate only through the eigenfunctions and eigenvalues. So, result of any measurement will always be eigenvalue corresponding to some eigenfunction. The only question which is left then, how do we define the eigenfunction that will give an eigenvalue which will be the result of the measurement? Because there are many. Okay? And there is a procedure to do that. That's the kind of a little bit complicated part of the route number 2. But it's quite straightforward. So now, for the kinetic energy operator, I want to say that this Fn of these functions that are eigenfunctions of the kinetic energy operator are given by such expression, where x, again, in the range from 0 to 2. Okay? Sine function of n pi x, where n is an index that goes from 1 to infinity. 1, 2, 3, 4, and so on till infinity. Okay? And pi is the one that 2 pi r is the circumference of the circle, right? Or pi r square is this as an area of the circle with the radius r. So that pi, right? And then, well, there's a sine function. Now, why do I bring this up? Because these will be very important objects. They are eigenfunctions of the operator that we're interested in. So I will in a moment show you that indeed they are eigenfunctions. What is their value? Their value is that what we're going to do in the case number 2, we're going to expand the function we're given as a linear combination of eigenfunctions for the operator that we're interested in. Okay? And that expansion is very important because that expansion will give us the coefficients in front of the eigenfunctions. Okay? And these coefficients, they're absolute squares, will define the probability to obtain, as a result of the measurement, eigenvalue lambda n, right, when we measure function psi. Okay? So in a sense, the situation is the following. Like you're going in the crowd, right, and you have a couple of friends, like say 10, 7 names that you well know, and it seems like there's a person in the crowd who look like your friend, right? And really, the time is tight, and you want to like call because the guy will leave, and you're thinking through the name of your friends, and you really want to meet the guy, talk, because you haven't seen him for some time, right? But the process is not deterministic. You don't know exactly what's the name, so which name to call, right? So probabilistically, you decide who looks more like a person among the names that you remember. And that's what is happening here. Essentially, this is the person you see in the crowd. These are the names you know, and these are the probabilities, in a sense, of that the person who you see look like the people you already know from the past, right? And so when you decide, okay, to call a name, there is a probabilistic process that is defined by, say, whichever coefficient is the biggest, that has the bigger probability, the name among the friends that you remember, that name will come out with a larger probability in that process. But it's not deterministic because the person in the crowd doesn't look exactly like someone you remember. He looks like this couple of people, right? And you don't know exactly which name to call. Well, that's what is happening here in quantum mechanics. When the wave function that is given is not an eigenfunction of the t, of the operator that we're interested in, yet the result will always be an eigenvalue corresponding to some eigenfunction. And what we can do in quantum mechanics is we're doing this expansion of the wave function that we are given through the functions that are eigenfunctions of the operator that we're interested in. Okay? And I will clarify how do we do this expansion, but the point is that this expansion gives us coefficients. And this coefficient squared gives us probability. Okay? And that's all we can know from quantum mechanics. Okay? So if a wave function is not an eigenfunction, then there is no way to say with 100% what will be the result of the measurement. Okay? So that is uncertainty that quantum mechanics has in it. And that uncertainty comes from the fact that the function you need to deal with is not necessarily an eigenfunction of the operator that you're interested in. Okay? So that's the drama here. That life gives you a function which is not an eigenfunction. What do you do then? Right? So it's like you see the person in the crowd, he looks like your friend, but you don't exactly know which one. Right? And you don't have more information. And you don't have much time. So you just go probabilistically and call a name out of the list of people who look like him. Right? And so that's what we do in quantum mechanics too. It's just this is what quantum mechanics provides, essentially. It allows us quantitatively formulate what the probability is. Okay? So when you do this experiment with your friend in a crowd, you don't know exactly what the probability of getting the right name. Right? But the quantum mechanics, it's exact science, so it gives you probability exactly. So that's the difference. Okay? But it's still a probability. It's not 100%. Now, this is kind of a general overview of what's going on. Now let's get to the aspect, how do we do this? So now we have these functions, which are eigenfunctions, and this can be easily shown. This can be easily shown by applying the operator. Right? We take an operator we apply to functions fn, t times fn, and we will get lambda n fn. That's the plan. Let's see whether that's the case. Well, right away, t has a double differentiation, right? You differentiate sine function twice, what do you get? Sine function, right? Because first time you get cosine function, second time you get back sine, right? So that's why there is a big hope that these functions are eigenfunctions, because t is a double differentiation, right, with some extra constant. Okay. So when you differentiate sine, first time you get cosine with plus, but when you differentiate cosine, you get minus sine. So there is a -1 sine that cancels this minus, and the result is positive, h bar squared divided by 2m. Then every time we differentiate, we get n pi divided by 2, and we differentiate twice, so there will be n pi squared divided by 4, multiplied by sine, n pi x divided by 2. Right? So after this differentiation, we got back function that we started with, and this is our eigenvalue, right? Note that it depends on the subscript n. So depending on what n do you have in sine, the eigenvalue will be different. Okay, it has this h bars, masses, pi's, and what is important, n. Okay, so these are possible results of the measurement. Now, in order to do this expansion, we talked at the previous lecture that we are operating with functions like with vectors, and we do obtain the coefficients of the expansion by essentially doing a projection. If you have a vector, right, and you have basis vectors, in order to find the coefficients of vector v, written as e of x, e of y, what do we do? V vector is, say, v of x times vector ex plus v of y times e of y. Right? How do we obtain these numbers? We project, right? So what does the projection geometrically means is that we put the, we essentially measure what is the distance if we put the perpendicular line, right? And formally, that corresponds to taking the inner product of vector v with ex, with the basis vector, the projection on which we're interested in, right? So this is going to be vx. So the same thing with functions. Now, psi is equal to cn fn, right? So this is our vector v, analog of vector v, and fn's analog of the basis vectors ex, right? So how do we get coefficient in front of any function n, right? So we project, and projection in quantum mechanics is pretty much algebraically, this is the same thing. Say if we're interested in some kind of coefficient k, just to have a different letter, because n is reserved for this, n is running from 1 to possibly infinite numbers of the coefficients, right? It's the space of functions is infinite. That's the one difference between the vectors and functions. That, but that's not really a big importance for us. All right, so we do the projection the same way we did the projection on the vector, on the basis vector. And if our functions are so-called orthonormal, then doing this projection will give us Cn, Fk, Fn, right? So k here is any number. I just use letter because I don't want to specify the number right now, but it can be 1, 2, 3, anything, right? And the way we can get coefficient Ck out of this is when these projections of functions are either 0 or 1, and 0 when the k is not equal to n, and 1 where k is equal to n. Right? In such situation, then in this sum, you get only 1 term when n is exactly equal to k, and that will single out one coefficient for us. Okay? And in all other situations, we will just get zeros. Okay? So this is the genius of Fourier. Essentially, before Fourier figured out how to find these coefficients by making such projections, if you think about this problem, writing one function as linear combination of other functions is not a trivial thing, because how do you find the coefficients? How do you find the coefficients if you want to write the sine function as a linear combination of polynomial functions like 1, x, x squared, x cubed, and so on and so forth? So how do you do that? No one knew. And then Fourier found this nice analogy with vectors, and he said, well, why don't we work with the functions where we define inner products of function with this function, like two vectors, and then everything becomes like linear algebra, essentially. It becomes the same way we found the coefficients in vectors, we find the coefficients for the functions as a linear combination of other functions. Now, the only condition here, which is a very important condition, is this one, that the functions we work with, they must obey this relation that the system of function, you pick first function, you pick a second function, and their inner product is 0. You take any function and take the inner product with itself, then the answer is 1. Right? So this set of functions are called orthonormal functions, like with vectors. Okay? Now with functions, we need to define what the inner product is, and we did this in the previous lecture. So that's Fk Fn is always the integral from minus infinity to plus infinity, Fk star x, Fn x dx. Right? So instead of summing the components like in vectors, functions are represented as like inner product of two functions is the integral between the two functions. Right? So that's the way we generalize their inner product to functions that are treated like vectors. Okay? Okay, once we've done that, we checked that the function that that I suggested, they are eigenfunctions of the kinetic energy operator, right? So it makes sense to expand whatever function you are given as a linear combination of those functions. But now to make the expansion this way, we need to make sure that the functions are orthonormal. Because if functions are not orthonormal, these products are not going to be just 0 and 1, they can be anything potentially. If you have two random functions and you take the integral like this, they can be the integral can be anything, right? So let's make sure that these functions are indeed orthonormal, that these integrals are indeed 0 and 1 if k and n, well, it's 0 when k and not equal to n, and it's 1 when k equals to n. Okay, so we check that the functions are orthonormal. How do we do that? Well, we know the function, right? So this integral of fk, and they're real, so the stars are not important for now, right? So these stars, they are important only for functions that have complex parts. So what we want to show is that functions are orthonormal. So so what is this integral? Well, this integral is, and let me, in my notes I have n and m, so I will use n and m so that I will not confuse you. But it's the same thing. K, n, m, it's just letters, essentially. They used to not to name a particular number. It's like when I say n instead of a number, it's like I'm saying a student instead of naming a name, right? So if I want just refer to a generic student, I will use word student instead of a particular name. So the same thing here with the indices. N and m, these just the numbers which I don't want to name, because by naming that n is equal to 1, say, I am restricting myself and my consideration to a first function. But I don't want to restrict this. I claim that this is general. So no matter what n is or what m is, what I will show is that this integral will be 0 or 1 for any n and m. Okay? So that's why I'm using letters, not to confuse you, but rather produce a more general result. Okay, so this integral, if we put the functions inside, is sine of n pi x divided by 2 sine of m pi x divided by 2. Okay? And so since we considered the whole range, but the functions are from 0 to 2, really this integral is also considered from 0 to 2, because the functions that we introduce, they are sine functions only in the range between 0 and 2, and then beyond that range it's just they're zeros. Alright, so how do we take the integral like this? Any idea? We need to take the integral. So what do we use for that? Well, it's a product of two sines, and we know that the sine of alpha times the sine of beta is equal to 1/2 cosine of difference minus cosine of sum. Okay? And so if we substitute the product of sine by the difference of two cosines, then we can integrate cosines. We know how to do that, right? Integral of a cosine is a sine function. So we do that, and the integral here, this is like intermediate step Well, the integral will be of dx 1/2 cosine n minus m by x divided by 2 minus cosine n plus m by x divided by 2. Okay? So now the integration of cosines is relatively straightforward. And so what we get at the end is indeed, well, it's all in the notes. Notes are posted. So I don't want to repeat what is already written in the notes because it will take time. These integrals essentially are equal to either 0 or 1. 0 when n is not equal to m, and 1 when n equals to m. So by just doing this straightforward calculus of the one-dimensional integrals, it's easy to show, if you know how to integrate, that functions are orthonormal, right? So if we define the inner product of two functions as an integral, then indeed we get these relations. And then you can use these functions to expand any function psi as linear combination over these functions. And the coefficients can be found as the integral of original, or like this set of functions with original function, right? It's very straightforward and simple. Okay? Now, the only thing that is left to be checked is that our function that was given is a normalized function. Because if the function is not normalized, you can do this expansion for sure, no problem. But these coefficients, absolute square of them, they, when you sum them, they are not going to be 1. So they cannot be considered as a probabilities. Because the origin of this problem is that the function that we started with wasn't normalized. Okay? So only for the normalized function, the sum of the absolute square of the coefficients is 1. And that's why if we want to use the coefficient squared as the probabilities to find in experiment the values which are corresponding eigenvalues for the functions, right? Then we need to make sure that the function we're dealing with is the normalized function by itself. Okay? And so how do we do that? The procedure is kind of straightforward. We have a function, and so we have a function was written here, and then we check that this integral is some number, and if it's not 1, then we divide by square root of that number, the original function, to normalize it. So let's find what's the value of this integral. So we integrate from 0 to 2. That's where the function is non-zero. And we integrate x minus 2 squared dx. So this is real function we can skip the absolute value, and then have an integral to take, x to the fourth minus 4 x to the cube and so skipping the algebra that is already given in the notes, this is a simple integral, and the value of that integral is 32 over 30. Okay, so this is not 1. That means we need to normalize function in order to proceed in this problem. So the normalized version would be function divided by the square root of this number, which is 3230, right? And so that means normalized version of this function will be square root of 30 divided by 32 multiplied by x minus 2 or 0. This is within the range 0, 2. This is outside of that range. Right? So now we have a function that is a proper function. It's still not an eigenfunction of the kinetic energy, but now we can expand it as linear combination of our orthonormal functions, fn's, find the coefficients. Square of those coefficients will be probability densities to find in experiment values which correspond to the functions. Okay? So how is this done? Well, as I wrote already, the coefficients are the integrals, and all action again happens between 0 and 2. The outside of the range, it's well, the functions are 0, so there is no point of integrating there. But if functions were outside of 0, 2 range, then we would integrate from minus infinity to plus infinity in general. Right? So then these coefficients are taking the normalized function multiplied by corresponding eigenfunctions of the operator, right? And so this gives us coefficients. Now this integral can be calculated because we know what the function psi n is and what the eigenfunctions are, right? So these are sine function, this is polynomial function, and the integral of the sine times polynomial anyone can take, essentially. So let me write down the integral. Square root of 30 divided by 32, x minus 2, and then sine of n pi x divided by 2. Right? So this integral is a number, and I can write down after some algebra you can obtain that the coefficient is 4 square root of 15 cosine n pi minus 1 divided by n to the cube pi cube. Okay, so that's the expression that you can obtain yourself at home by taking this integral. And one thing for those who know trigonometry is that If you have even ends, then the cosine will be equal to 1, and so the coefficients will be 0. If n is odd, then the cosine will not be equal to 1, and the coefficients will be non-zero. So that's something extra you can figure out knowing what the cosine is. But now this coefficient squared, so they are real numbers, you can just square them, but the proper form would be the probability is equal to the absolute value squared, because these coefficients could be potentially, the coefficients themselves can be complex, right? So this is a probability to find lambda n's, which we already found what the values were. Right, so these are the results that you can obtain in an experiment if you start with a wave function like this or like that. They have the same spatial dependence, just a normalization, that's the difference. And the probabilities to find these results in the measurement process are given by this coefficient squared. Okay? So how does this look? Pretty straightforward. Okay. So what's the hardest part? Yeah.
How do you determine
Fn of x is determined from the condition that you have an operator, right? In this case, we're looking at the kinetic energy, right? So you know the operator. And then this condition that the functions are eigenfunctions, this condition usually gives you a differential equation that you can solve. And in most of the situations, you won't need to find the functions. They will be given, because this problem, as any differential equation problem, is difficult most of the time, and unless it's very simple case, then finding the eigenfunctions is not a trivial task. But they will be given. From you, what is required is clear understanding that chain, that logical chain. You have a property has an operator has an eigenfunctions and eigenvalues. Now you are given a function and ask the question, what will be the result of the measurement of that property? And you need to define first whether this function that you are given is an eigenfunction of the operator or not. If it's an eigenfunction, then things are simple. All you do is to find eigenvalue corresponding to that function. If your function is not an eigenfunctional operator, fear not, there is a procedure where you expand your function as a linear combination of eigenfunctions of the operator, which are given usually, and then the expansion finding the expansion means you find the coefficients, right? And the coefficients, they give you, if you square them, take an absolute square, that gives you probabilities to obtain an experiment eigenvalues corresponding to the operator, right? And so these are the results of the measurements. There are many, usually, but their probabilities are defined through the coefficient, through the absolute squares of the coefficients. Okay?
So just to review,
yeah.
we're going to be given some wave function in defined in some element area.
Right.
And we're going to be asked to take a look at some of the different measurements and predict the probability of something.
Right.
So the first thing that we
Yeah. Yeah, you can start with that. Again, there is a prescription through normalization, and just to not to confuse you, but give you more flexibility, there is a way to kind of to avoid explicit normalization, right? So there is a way to sometimes. Well, you don't need to you don't need to always normalize, but for this type of problems, it's kind of easier to normalize. Yes.
Make sure your function is normalized, and then you have to see if you didn't put the ordinality check in your basis.
Right.
So if the Fn is given, then we would do that next.
Unless it's stated explicitly that they are orthonormal, so don't worry about that.
Okay, cool. And then after that, you just do your integration method to arrive at the Cn.
That's right.
Scale back to that method,
One correction: Cn is not the result of the experiment. Lambda n is, right? So, but Cn squared gives you the probability to find corresponding lambda n. Now you can kind of make the first branch. You can see actually the first branch as nothing but the special case of the second one. For the following reason: if your function psi is actually an eigenfunction of an operator, that means that psi is equal to a particular f of k, fk, right? And if it's the case, that's your expansion. And that means this expansion is truly written like this. That means all the coefficients are 0 but 1, right? And that one coefficient is in front of the function that is equal to your function, right? So therefore, in this branch number 1, it's a special case of branch number 2 where you have only one coefficient which is 1 and all others are 0. Therefore, it's determined from the coefficients that the probability will be 1 only for one event and 0 for any other event. Okay? But that's a special case. It's not a general case. Okay? Right, it's like with the crowd example, would be you have only one friend. And that's the only friend you either recognize or not. That's it. Okay? So now, this is probably the most difficult, the most involved problem I just showed you, where you have a function which is not an eigenfunction, and it's written. It's not written as a linear combination. It's written like something, and you need to find the coefficients in front of the eigenfunctions, right? So that is probably the hardest case. Now, in the left time, I would like to show you a situation which is somewhat easier, and also will be given in problems. So let's say the situation is the following. The function you are given, say it's still about kinetic energy, f's are still the ones that are given you, but let me change the function of the system. The function of the system, say, is given as an expansion. Right? So this is easier case because the function is given an expansion of eigenfunctions. And, well, the first question, whether this function is an eigenfunction of the kinetic energy operator. Well, probably already at this point you have an intuition that the answer is no. And it can be, even without going to the calculus, even without differentiation, and that can be shown just algebraically. By algebraically, I mean we know the relation when t acts on fn, it produces lambda n fn, right? And we have two types of functions, 1 and 2, in this expansion. And of course, lambda 1 is not equal lambda 2 because we calculated what lambdas are. They're given here. And if you put n equals 1 or n equal 2, the values of lambda will be different, right? So then, if t acts on this linear combination, the easy way to treat this action is t acts on the first function multiplied by a constant, plus then t acts on the second multiplied by the constant, because t, it contains the differentiation operator, and that operator is linear. So essentially what I said is the manifestation of linearity, that the operator acts on the functions separately, and then you can add the results and multiply them by constants. So the result will be 5 times t acting on f1 plus 3 t acting on f2, right? And we know what this is and what this is from just knowledge that the functions are eigenfunctions of t. And so then this is lambda 1 f1 plus 3 lambda 2 f2, right? And so since lambda 1 and lambda 2 are different, this cannot be written as some lambda multiplied by 5f1 plus 3f2. This is our original function f, right? Or psi. So we started with this psi, we acted with t. The action of t produced different lambdas in two different terms, and that's why we cannot write this now as one lambda multiplied by a function, because these two lambdas are different. Okay? So even without going into differentiation, simply because the function I gave you is written as linear combination of eigenfunctions, then action of the operator on that linear combination is very simple. You just act on every term. And one nice thing about eigenfunctions is that I said that operators don't change shape of those functions. But from an algebraic point of view, I guess the eigenfunctions are the functions where essentially action of the operator is the simplest. It's just multiplication by a number, right? So if you take any random function, operator can do random things with a random function. But when the operator acts on its eigenfunction, it only multiplies the eigenfunction by a constant. So that's one of the simplest possible actions you can think of, right? You don't change the shape, you don't differentiate, you don't add another function, you just multiply by a constant, right? That's why figuring out what the operator does to a function is probably, well, the simplest representation is when you write your function as a linear combination of eigenfunctions for the operator and then act on each term by the operator. Okay? So we've shown just right now here that if you have linear combination of two eigenfunctions, it's not an eigenfunction anymore, because when the operator acts, it makes the eigenvalues to pop up, and those eigenvalues are different. All right? Now, okay, so what's the next step? So what we would like to do is, well, the problem is the same. If you are given a function like this, what would be the result of the measurement for the kinetic energy for this function. Okay, and the next step is, let's just make sure that the function that we're given is normalized, so that we can work with it as like a normal eigenfunction or system function, so that can represent the probability density. And to have a normalized function, we again want to consider the psi square from minus infinity to plus infinity dx, and make sure that number is 1, and if it's not 1, then we divide the function, right? We divide the function by the square root of n to normalize. If it's 1, then this division is not necessary, of course. Now, again, as in the case of checking whether the function is eigenfunction or not, normalization process is also facilitated by the expansion that we have. I'll show you why. So essentially what this is its inner product of the function with itself. And every function is a linear combination of eigenfunctions. Right? Now, without going into integrals, this will be very easy, because the inner product is a linear kind of function, bilinear, by the way, so you can take the coefficients out and write this as 25, 5 times 5, f1, f1, plus 3 times 515, f2, f1, plus another 15, where f1 is here, f2 is here, plus 3 times 3, 9, f2, f2. Okay? So now the easy part is that I know already what these inner products are, because they're inner products of eigenfunctions, and we know if you take inner product of function with k and n, it's always going to be 0 or 1, depending on whether k equals to n or k not equals to n, right? So going here, f2, f1 will go to 0, f1, f2 will go to 0, f1, f1 will go to 1, f2, f2 will go to 1, right? So no need to integrate, because we already used the linearity of the integral that is written here, and the fact that the functions we're operating with, they are orthonormal, right? So again, the expansion in terms of orthonormal functions, it makes calculations much simpler. You skip all the integration, you just do the algebra. I mean, by algebra I mean you just use the relation between the quantities instead of doing a calculus where you need to differentiate, integrate, that sort of things. And yeah. So what does this mean? That means that this number n, right, the inner product of function with itself, is 25 plus 9. Right? 25 plus 9 is what? 34. So that's the number. And 34, of course, is not 1. So that means we would need to normalize function by dividing it by square root of 34. So doing this. Okay? But this is easy. All we do is we take the expansion there, 5 divided by square root of 34, f1 plus 3 divided by square root of 34 f2. And this is our function now. Okay? Okay. So function is ready. Okay, so we know lambda n's will be the result of the measurement, and the probability of getting lambda n is cn squared, which is absolute square of psi n times fn star of x dx, right? Now tell me, what are going to be the results of the measurement for this function? Again, things are much simpler when you are given this expansion, because expansion is already given. Yeah. Let's first focus on what will be the results of the measurement, not the probabilities with which these results will be obtained, but what are the measurement? Like, you measure this function, and what are the possible outcomes of that measurement? That should be an eigenvalues associated with the functions which are present within that function. So this function is an expansion over eigenfunctions, right? And the coefficients of those eigenfunctions, they determine the probability of getting eigenvalues corresponding to these eigenfunctions. Okay? So now, as you can see, only eigenfunction f1 and f2 is present. Others, you can always write that there is f3 present, which is multiplied by 0 coefficient, right? So the only two results of the measurement will be lambda 1 and lambda 2, because the coefficients in front of f1 and f2 are non-zero. The other coefficients are all 0. So result of lambda n, where n is not equal 1 or 2, the probability of that will be 0, because there is no f3, 5, or 6, right? So there are no other f's. There is only f1 and f2, and so therefore only coefficients in front of f1, c1, and the coefficient in front of f2, c2, will be non-zero, right? And so therefore the only two results of the measurement possible here is lambda 1 and lambda 2. And the probabilities of getting lambda 1 will be this coefficient, which is c1 squared, right? So what is it? 25 divided by 34. That's the probability of getting lambda 1. And the probability of getting lambda 2 is 9 over 34. That's the probability of getting lambda 2. Okay? So, and the probability of getting anything else is 0, because there is nothing else. Only these two functions. So that's why this case, that's pretty much it. That's the whole problem. Like, I gave you the expansion of a wave function in eigenfunctions of the operator that we're interested in, right? Then the only thing which you need to figure out, okay, it's easy to figure out that if there are 2, 3, or more eigenfunctions are present, then this linear combination is not going to be eigenfunction. That's easy to see through the algebra. Then you normalize it using the fact that eigenfunctions are orthonormal. They can be made that way always. And then normalization process is very simple, algebraic. And then once you normalized, you have a function where you have a coefficients and those coefficients will be the only they will be determining the only few events that are possible when you measure, right? Because the only few coefficients that are non-zero. You can of course go through the formal derivation, and it will give you of course exactly the same answer. The formal derivation would be the following, that in order to find the Cn, this is the integral of psi n times Fn star x, right? And then this is the integral, and here we have alpha will be that coefficient in front of F1, plus beta will be coefficient in front of F2, Fn star x dx, and this will be alpha integral of F1 Fn dx plus beta integral of F2 Fn star dx, right? So this is only non-zero when n equals to 1, and this is non-zero when n equals to 2. So therefore, the C1 would be alpha, and C2 will be beta, right? So that's what we got at the end. You could do this way, or you can just notice, okay, you already have that expansion, so there is no point of actually making these integrals because they all will be 0 and 1. But as in any math problem and in any problem that are new to you, that it helps to actually arrive to the same answer in multiple ways. That's how actually we do science, when we are not certain about kind of what is the right way. We arrive through different routes, and if they give the same answer, that means we're on the right track. But if they give in their own different answers, then that means that something else needs to be clarified, or we kind of need to figure out things more. Right, so then I guess everyone makes mistakes. My suggestion always to check, well, to have at least one or two, well, more than one ways of arriving to the same answer, and it's really hard to make different mistakes that will give you the same answer. Eventually you will see that, oh, somewhere you made a mistake if the two equivalent ways give you different answers, right? So that's the way you can kind of always check that you doing the right thing. And in general, if you are given any, I guess if you, this problem can be generalized, and if you are given, say, some coefficients like alpha Fn plus beta Fm gamma Fk, right, where Fn, Fm, and Fk are eigenfunctions of the operator of interest, right? Then, and they say you have orthonormal functions. I use delta Kronecker symbol. Here delta nm is when it's equal to 0 when n not equals to m, and equals to 1 when n equals to m. That's just a shorthand notation. Then psi will be just the alpha square plus beta square plus gamma square, right? So then to normalize the function, you would simply divide alpha by the sum over squares, Fn plus beta Fm, again sum over squares, and then gamma divided by, again, sum over squares. Right, so that will be a normalized function, And from this, you can easily find that the coefficients are just these ratios, right? And the results of the measurement will be either lambda n, lambda m, or lambda k. And the probabilities will be given by the square of the coefficients, right? Absolute squares if they are possibly complex. Okay? Now, this should be relatively straightforward. Now, this second case, when your function is not an eigenfunction of the operator, and we kind of make a measurement. According to quantum mechanics, what happens when measurement takes place, you have a wave function, say, of this kind, and you measured and you produced, say, lambda n, right, as a result of the measurement. And quantum mechanics doesn't study what actually happens when measurement takes place, because this is a small system, say electron, right, which has a wave function psi. And in order to measure, we couple or connect the electron to large macroscopic apparatus. Compared to electron, apparatus is huge, right? And there is a process that happens when the apparatus is connected to the electron. And that process, well, first outcome is that the kind of the arrow on the apparatus shows lambda n, right, as a result of the measurement. But the wave function of the small object, what happens to that, it's actually quite difficult to analyze this in global scale, because you have quantum mechanics and something that is described by classical physics. In order to figure out what's going to happen when you couple things to this wave function psi, we need to apply quantum mechanics to the large system as well. And so that goes beyond the course, the current course. But as a postulate, usually people formulate that whenever we get the eigenvalue lambda n, as a result, what happens to the wave function, it collapses to the eigenfunction fn. Okay, so you had a system in psi in this kind of wave function. When you measure and you get the result, what you obtain, what happens to your wave function, it became fn. Okay, so you change the wave function of the object that you measure. So that's the postulate of quantum mechanics. And understanding why is this happening goes beyond this course. So right now I will just postulate that that's what reality is, right? So if you measure and you get the lambda n, then the function collapses to function fn. So it's not anymore a linear combination of three functions, it's just one function fn. So now if you measure it again, what's going to happen? You will get lambda n again, because your function now is an eigenfunction, right? And the eigenvalue is lambda n. And the probability of finding lambda n is 100%, because your function already, after first measurement, collapsed to the eigenfunction. Okay? Here, finding lambda n, the probability of that was alpha divided by alpha squared plus beta squared plus gamma squared, right? So that was the probability to find lambda n. We found that by, well, normalizing function and looking at the coefficient, right? But after, this is the first measurement, but if you do the measurement again, you collapse, you measure the collapsed function, and therefore the coefficient will be 1, so 100% you get the same answer. Okay, so that's kind of the situation with measurement. Now, how do we characterize still this uncertainty in the measurement? Usually when we talk about uncertainty, the reasonable experiment would be I make millions of copies of the system and start measuring. In order to say if I want to check that the probabilities that quantum mechanics predicts are correct, right? So this is the number that quantum mechanics predict. How do I check that in an experiment? Who knows? Maybe quantum mechanics is wrong. So how do I check it? As always, if the theory is right, it should predict something, and also it should predict how to check that prediction, right? So how do we check that this prediction, the probability of finding this particular value, is correct if we write it this way? So experimental setup would be creating large number, million, billion, no, like really large number of identical systems, right? All having the wave function psi, and start measuring the kinetic energy. Okay? So there are only three possible outcomes in this case: lambda n, lambda k, and lambda m. Right? And we can make a histogram, right? Lambda n, lambda m, lambda k. And here the number of times, if we measure millions of systems, we created array of millions of systems, and we start measuring. Of course, every time we measure, we do the collapse. There is no point of measuring it again, right? So that's why we create millions of systems, so that we can check this prediction. We want to work with a regional function, okay? And so say we start making a histogram as a result of our measurements, and we can get, say, 30% getting lambda n. So it's like in 1/3 of all the cases you end up with this result. Say, let's make it 20% lambda m and 50% lambda k, right? So that what this histogram would mean, that this number should be about 0.3, right? To have 30%, the probability should be 0.3, right? So if this number is 0.3 and then we measure in experiment and we get 30% of the cases lambda n, that means our predictions are correct. That's how we kind of check ourselves. And just as the last thing, of course, in any experiment like this, what people are, well, like, how do we characterize this somewhat random distribution? It's by average and standard deviation, right? So how do we find average? In quantum mechanics, there is an easy way to find average. And it turns out you don't even need eigenfunctions for that. You can go through the eigenfunctions, or you can skip the eigenfunctions. So first, simple way. How do we characterize average? Average kinetic energy is equal to this expression. What is this? This is just a convenient way of writing integrals. Okay? So you don't even need to normalize wave function for this. Okay? That's what I was referring. that sometimes we don't even need to normalize wave function. Normalization actually is done here implicitly. Why? Because the denominator is just essentially n, right? And in numerator we have two wave functions. You can think of this expression as each function is divided by square root of n, right? And so this is pretty much the same as using the normalized wave function. Okay. So you can either normalize the wave function and use this somewhat simpler expression, or skip the normalization and use this expression. Okay? And they are equivalent. So this is average, and average why does this average make sense? Well, from the point of view of this expansion, right? If we say we have a wave function, like here, let's use a simple example, right? If we have a wave function which has only two components, and the probability of finding each component is given by coefficients, right? So then the average lambda must be probability 1, lambda 1, plus probability 2, lambda 2, right? This kind of makes sense. If the only two results out of this wave function you can have is lambda 1 and lambda 2, and probability p1 and p2 are coming from the coefficient, that's the average, right? So now I will show you that this average is the same as pretty much this average if you put instead of psi, of course, the original function. So why is that? Out because p1 is c1 squared, lambda 1 plus p2 is c2 squared, lambda 2, right? Now I can always substitute lambda 1 and lambda 2 by the following. By f1 t f1, and lambda 2 will be substituted by the same thing but with f2, right? Because when t acts on f2, it will produce lambda 2, and f2 integrated with f2 will give you 1. So overall it's lambda 2. Okay, and then if that's the case, then this can be substituted by psi n t psi n. Why? Because simply psi n is c1 f1 plus c2 f2, right? And then psi n t psi n is equal to f1, essentially f1 c1 plus f2 c2 t c1 f1 plus c2 f2. Right, and then when t acts on each of these terms, it will produce corresponding lambdas, and f1, f2 terms will disappear because they are orthogonal, and the only two terms which will be left is f1, f1 and f2, f2. Right? So, long story short, these two definition of what average is, either you sum the normal the eigenvalues with corresponding probabilities, which is a more natural way of thinking of what should be the average result of the measurement. If in measurement you can obtain lambda 1 and lambda 2 with probabilities, p1 and p2, defined by the function, right? So then if you sum, that's the average. And this average you can show algebraically is equivalent to just taking the function, forgetting about eigenfunctions, and making the expression like this. Okay? So you don't even need to go to the eigenfunctions to find the average. That's the beauty of this expression. And if you go to the eigenfunctions, then you will get equivalent expression. Okay? And we'll talk about standard deviation next time.